the Dirac, the properties of Dirac spinor and of the Dirac equation. So we spend quite a bit of time understanding why is it Lorentz invariant and how to build Lorentz invariant and covariant quantities from two spinors, and we saw that the right conjugate spinor contains a gamma 0 matrix. So this is Dirac conjugation operation. So today we'll continue studying the Dirac equation. So let me write it down again. So it's really easy to write down the Lagrangian for this theory. So the action will be this one. So psi and psi bar should be thought of as independent variables, and it's pretty obvious that if you take a variation with respect to psi bar, then what you get is the Dirac equation. So what symmetry is this? A theory with this Lagrangian has? Well, one symmetry is Lorentz invariance that we discussed at length yesterday. But there is another symmetry which is also pretty obvious from the form of the Lagrangian. So if you take psi and change its phase, and obviously the conjugate spinor should have its phase changed in the opposite direction, then this will be a symmetry of the Lagrangian, because it is bilinear in psi bar. Okay, we can apply a Noether's theorem to this symmetry. We can write it first of all in the well, let me see, in the infinitesimal form. So delta psi is equal to I epsilon psi. Delta psi bar is minus I epsilon psi bar. So from that, we conclude that the generator of this symmetry acts simply by multiplying with an I. So L psi is simply I times psi, and L psi bar is minus I psi bar. So this symmetry is an internal symmetry. You see, it doesn't act on the coordinates. It only acts on the fields. And then we may apply the Noether's theorem. So again, it's a very simple calculation because, well, in the Noether's theorem, we should take a variation with respect to the derivative of the field. So in this form of writing the Dirac Lagrangian, it only depends on the derivative of the psi. So the Noether current will then be equal to, well, the derivative with respect to d mu psi, which is psi bar, times I, multiplied by the generator acting on the psi bar, which is minus, on the generator acting on the psi, which is I psi. And so what we get is up to a sign, psi bar, gamma mu psi. So this current is conserved. And later we will interpret this current as electric current. So the question is why? And indeed, it need not be an electric current. Just in the theory that describes electrons and positrons, this will be what we call usually the electric current. In some other theories described by the Dirac equation, it has a different interpretation. For instance, if for neutrinos, which are neutral particles, but which are described by the Dirac equation, this will correspond to the lepton number. So anyway, this is a conserved current in the theories described by the Dirac equation. So the density, so the charge associated with this current is the integral over the three-dimensional space of the zeroth component of this current, which is the charge density. And the charge density, as you can see, is just psi dagger psi. So the charge is then equal to psi dagger psi, which we started off with yesterday and showed that this is not really a Lorentz scalar. So from here you see that this is actually a zeroth component of the 4 vector, so it has the right transformation properties to be the charge density. Yes?
What is the charge associated with the Lorentz invariance?
Okay, so there is a charge associated with translations, which is the energy momentum tensor. So the charge associated with rotations and Lorentz symmetries is the angular momentum, but it's constructed from T mu nu by the formulas that they are in the notes, but I haven't written them.
How about Lorentz boosts?
Lorentz boosts is a bit tricky because they actually don't lead to any conserved quantities because, so if you write the charge density, then you see that it's time dependent. So it's explicit time dependence compensates for the time dependence that comes from the fields. And in particular, t equals 0, I think it vanishes. So anyway, it's not really, it's a strange case where there is a quantity that whose divergence is 0, but it's coordinate dependent. And in particular, it's time dependent explicitly. It's like x0 times something. So, okay, so this finishes sort of general construction of the Dirac theory. But now, as we have the Dirac equation, we would like to study its solutions. So, we're going to just take this equation and solve it, which can be done by Fourier transform. So if you write psi of x as an integral of d 4 pi over 2 pi 4 e to the minus I px, and then some amplitude that depends on the momentum, so which is also a spinor. So then the spinor will satisfy a matrix equation P minus M acting on U should be equal to 0. So here, any variable with a slash corresponds to a vector contracted with the Dirac matrices. So P slash is equal to P mu gamma mu. It's just a notation. Okay, so it's a 4x4 matrix equation. Well, on the right-hand side, we have a 0. Therefore, this matrix has to be degenerate, otherwise it will not have any solutions. So what is the condition for this matrix to be degenerate? Yes?
Would you maybe explain why it must be degenerate for time solutions?
Because if you have an equation, some matrix times a vector is 0, then the determinant of the matrix should be 0 for it to have solutions. For so U is a 0 eigenvector of this matrix, so it should have eigenvalues 0. Some eigenvectors. What?
Degeneracy? I solved eigenvalue problems before, but why must it be degenerate?
Degenerate. Well, it's just the terminology, I guess. It's a matrix with 0 eigenvalues. It's called degenerate. So it has 0 determinant. So can you guess what is the condition for it to have a 0 determinant? Yes?
My guess is the on-shell condition in this case.
Yeah. Yes, of course. So the condition that this has 0 determinant. In fact, there is a formula for its determinant that you can check. Is that this is p squared minus m squared squared. The condition, so this equation is solvable. So determinant must be equal to 0. And this is equivalent to the condition that p squared equals m squared. Another way to see that this is a necessary condition is to multiply. So this is one way to see. Another way is multiply by p slash plus m. And then use the same trick that we did when we derived the Dirac equation. So this times that is just p squared minus m squared. And so this is just a number. So number multiplying this vector should be 0. So it can only be only have solutions when this condition is satisfied. So the solutions they exist only when p is on shell. And let's find how they look like. The easiest way to do is to consider first some particular case. And so as such, we will take the case where P has obvious compoundings that correspond to particle at rest. So consider first the solution that describes the particle, Dirac particle at rest. In fact, this is not really a serious restriction because of Lorentz invariance, we can always choose a frame in such a way that just go to a rest frame of any particle, and then the form momentum will have this form.
So we're not considering all possible.
Well, the fact that you got the mass shell condition with this particular mass already means that this particle has mass m. So m is more or less clear from the analogy with the Klein-Gordon equation should be the particle's mass. So now what we are going to construct is the particle's wave function. So let's start with the rest frame. And then, okay, so you see that what we need to know is what is gamma 0. So gamma 0 is the off-diagonal block matrix. And then we can write the Dirac equation. So the Dirac equation then will have the following. In this block form, it will have the following structure. Well, let's not write P here because it's for a very particular thing. So you see immediately that indeed this matrix has half rank. Okay, so if you write U as in terms of 2 by 2 blocks, psi, say nu, and eta, then the two equations that you obtain by substituting it in the equation are just one and the same equation. So there is a half-rank degeneracy. And actually, the equation that you get is simply that psi is equal to eta. So the solution, therefore, is any spinor whose upper components are the same as lower components. In other words, it has two-dimensional space of solutions. So which we'll denote by US. So we'll label them by index that takes two values. Where psi s should form a basis in a two-dimensional space of upper or lower spinors. So we can take psi s, psi 1 to be a 1, 0 vector, and psi 2 to be a 0, 1 vector. Now, this normalization is chosen because at the end we will need to use this in the expansion of the field, and this vector has relativistic origin. So we discussed at some point that in relativistic field theory, the normalization of wave functions should be different. It differs by square root of the energy from non-relativistic unit normalization. So this has the same origin. Now, what these two solutions mean? So what is this S label? What do you think? What is its physical meaning? Sorry? Not quite, because there will be a label that distinguishes particles and antiparticles. It's not this one. Yeah, this is the spin label. So, yes?
Can I just clarify? Sir, you're talking about the normalization we had. So are you saying that U is Lorentz invariant?
No, U is not Lorentz invariant.
So what's the purpose of the normalization then?
So this is, first of all, this is a very particular solution in a very particular frame. So U depends on P in general. of course, Lorentz transformations act in a very non-trivial way on U. But okay, at this point we can choose any normalization, whatever normalization we want. Let's choose just this one. Okay, so how to say that this is spin? Well, as you remember, the spin operator the non-relativistic spin operator was given by the matrix that had sigmas on the diagonal and zeros off diagonal. So obviously the spin of so first of all, it's clear that we diagonalize as Z by choosing this particular basis, and also that S Z acting on U1 is plus 1/2, and S Z acting on U2 is minus 1/2 of MC2. So this shows that that these are two spin polarizations of a particle at rest. So these wave functions, they describe a particle of mass m, because it satisfies the mass shell condition with mass m. It is, this particle is at rest. We've just chosen the form momentum to be to correspond to a particle at rest. And it has definite spin projections on the z-axis. So if you choose the wave functions in this particular way, choose the basis in this way. Okay, so what remains to do is to just boost this solution to any particular reference frame, or start from the equation that contains an arbitrary form momentum on shell, and then find a solution that would reduce to this one in the rest frame. So let me just write down the answer, because it's a bit, the derivation is a bit technical and is not really useful in any respect. To write down the answer, we will need a parameterization of Dirac matrices. So we may write them in a unified way if we introduce a fourth index on the Pauli matrices. So sigma mu then is equal to 1 sigma. Sigma bar is equal to 1 minus sigma. So bar is not really a complex conjugation. It's, it is what is written here. So it's just a definition. It's an independent set of four matrices. So then the Dirac equation is written like that. And then you see that the equation is solved as long as u left is related to u right. So again, we can choose an arbitrary U right. So that there is a two-parametric arbitrariness. We can choose U right as we wish, and then the equation fixes U left. So to make it all look like the solution at rest, when we set P to this particular value, we can set U right to be a square root of P P dot sigma bar times times what? Times CS. And then U left we find from here, and then using some relations between the sigma matrices, at the end we can write the general solution. So this is the general solution in an arbitrary frame. Square root here, so we need to take a square root of a 2 by 2 matrix. Square root is actually an ambiguous operation in matrices. So it's defined in such a way that for zero spatial momentum, this is just a unit matrix times M. So we take the sign of the square root as here in the algebraic way. Okay, and then we can this can be continued to arbitrary momenta by continuity. So that's it. This is the solution in an arbitrary frame. There are a few useful formulas. One is normalization of this solution. So if you take a Fermion conjugate of U and contract it with the Fermion conjugate of another U, but with the same momentum, with different spin, but with the same momentum. Then the solutions with different spin, they are orthogonal. And those with the same spin are normalized to the energy times delta SR. Well, this formula also has a nice Lorentz invariant interpretation, Lorentz covariant interpretation. Because you see on the right-hand side, we don't have a scalar. This transforms as a zero component of a 4 vector, the energy. And on the left-hand side, we have the quantity that transforms in the same way. Because this is psi-digger psi, as we saw, transforms as a zero component of a 4 vector. So if we want to have a scalar, we need to take the Dirac conjugation. And for that, we find indeed the scalar on the right-hand side. So these formulas can be derived in a very direct way. You just plug in the explicit solution and find and take, well, product of two vectors. But there is an indirect argument which shows that they should be like that. So because we know that, so for instance, in this formula, we know that the left-hand side is a scalar. It is the same in all reference frames. So we can compute it for this simple solution in the rest frame. And then we know that on the right-hand side, we should have 2m. So the same is true here. On the right-hand side, we should have the zeroth component of some 4 vector that in the rest frame reduces to m. and this is the particle's energy. Another useful formula is obtained when we take the tensor product of two solutions and sum over the spin index. And so this turns out to be equal to P plus M alpha beta. Again, there is a cross-check on this formula. We can apply the Dirac equation to it. Okay. So on the left-hand side, we get 0 because the Dirac equation acts on U, and U is a solution by construction. And on the right-hand side, we get 0 just because this becomes P squared minus M squared. Okay. So these are the basic solutions of the Dirac equations, but these are not the only ones that we will need. In the derivation, at some point, we assumed that the energy was positive. So you see that when we started with the rest frame solution, we assumed that mass, the 4 vector has a positive energy of, so this is the physical mass shell condition for some particle. But as we learned that in quantizing the Lagrangian equation, we also need negative energy solutions. They would describe annihilation operators in the Fourier expansion of the field. So this, well, the derivation goes exactly the same way. You just need to change signs here and there. Let me just write down the answer. So the solutions with negative energy, they contain a different sign in front of the lower component. So 8AS is again the same basis of spinors, well, of two-dimensional spinors. We introduced a different letter just to distinguish it from U. So this is just an independent solution of the Dirac equation. Well, its normalization conditions are also a bit different. And also another useful formula is the summation over spin. Okay, so yes.
In this case, for Vs dagger P Vs P equals 2EP delta SR, is EP as written positive or negative?
Negative, I suppose.
So
Let's see. let's check. So we can do it in the frame where P is where P has components minus M000. So then then V is equal to Vs is equal to eta S and minus eta S times square root of M. So then we can see that Vs bigger Vr is equal to plus 2m delta Sr, and V bar S Vr is so in this case we need to take, so this would be nu S minus nu S, and then gamma 0, and then the original spinner, then times m. So this will be equal to minus 2m delta SR. Okay? Because this matrix and gamma 0 interchanges upper and lower components of the spin. So here, this is understood as an algebraic value of the energy with the plus sign. So square root of m squared plus n plus p squared. So, well, having solved the Dirac equation, we can now quantize the field. So in principle, we should, to do it honestly, we need to write down the Hamiltonian, figure out what are the canonical variables, and then impose the canonical commutation relations and diagonalize the Hamiltonian. But we will not do this because the final result of this calculation can be obtained by a trick that we sort of saw in the quantization of the Lagrangian field. We just take all possible set of solutions of the Dirac equation and simply interpret the Fourier coefficients as creation or annihilation operators. And this will give the right answer. So in other words, we should write psi of x as a Fourier integral to ensure that it has that it solves the Dirac equation. We should insert the on-shell condition to distinguish positive and negative energy states. We need to introduce the step function. So the set of solutions is two-dimensional, as we saw, so we need to have the sum over S. And here, well, we can have arbitrary amplitudes that we'll call A PS multiplying the particle solution. So positive energy solution. And then there will be a coefficient that multiplies the negative energy solution, which we interpret as the creation operator. So this is the most general solution. We separated positive and negative energy parts in it. And then in quantizing the field, these coefficients are interpreted as creation and annihilation operators. Now, in contradistinction to the Lagrangian case, where this was one and the same operator, but I mean, these were complex Hermitian conjugate operators. Here, we really have to write down different operators. This is because the Dirac field is a complex field. So psi dagger is a completely independent quantity. If we were to relate these coefficients, then there will be some linear relationship between psi dagger and psi, and that we cannot, or we don't want to impose. So we want to keep these coefficients as independent. Therefore, Dirac theory predicts that there are two types of particles. So now we see that there is an antiparticle in the theory. And the antiparticle corresponds to the fact that, well, the field is complex, and we have to introduce two types of, so the creation operator that appears in the field operator is not conjugate to the annihilation operator of the particle. So their conjugates appear in the expansion of the conjugate field. Well, this is, of course, this formula is just a consequence of that one. So these formulas describe quantized Dirac field. And then they describe two types of particles. So what kind of particles these are? The claim is that these particles should be fermions. So in principle, no one told us that what kind of commutation relations we should impose. Commutation relations or anti-commutation relations. So what happens here is that if we impose commutation relations, we immediately, very soon we run into trouble with, say, the energy formula. So the Hamiltonian will not be positive definite, and so there will be other pathologies in this theory. So therefore, we are forced to impose the anti-commutation relations. So let me not explain why commutation relations do not work. There is the whole chapter in the textbook about this. So the correct way to quantize the Dirac field is to interpret it, the particle as a fermion, and then the ladder operators should satisfy anti-commutation relations. Then for the Hamiltonian, well, we get the expected expression with energy as the coefficient, and then the particle densities for all spins and all charges, or for particles and antiparticles. So for the momentum operator, we will have the same formula. Is the energy replaced by the momentum. So the new ingredient here is that we also conserved an extra conserved charge Q. So for which we get a little bit different expression. So it will again be expressed in terms of particle densities, but there will be a relative sign between the A oscillators and B oscillators. Yes?
To be clear, A Dagger and B Dagger are still creation operators, right?
Yes.
And should there be a delta RS in the anti-commutator expressions?
Yes. Thank you for reminding me of that. There's another question?
No, that was
The same. Yes.
So when we do quantize of the angle of field, we can the rotation relation of both the radiation annihilation operator of the momentum and also the rotation relation of the quantum field. So if there any that the anti-commutation relation of the quantum
Yes, exactly. So psi and psi bar satisfy some sort of simple anti-commutation relations, which leave you as an exercise to compute. So you can just use anti-commutation relations between A and B, and then the formulas of this type that would in principle allow you to compute the commutator of psi and psi bar.
So, are these? Can I like derive this from this anti-commutation relation of that one? I mean,
You mean start from the anti-commutation relations for the fields?
yeah. Like,
Yes, in principle, that would be the honest way to derive them. So the
so it's-
correct way to quantize would be to start with the Hamiltonian written in terms of fields, then identify the conjugate variables, psi and psi dagger.
So is this the reason why we try to quantize the quantum field in this way, in this formula, in order that so that this anti-commutation relation and also the anti-commutation relation of the quantum field can both be satisfied?
Yes, this is the way to see this formula. That's true. But it is, I mean, I took a shortcut. I just wrote it down by analogy with the Klein-Gordon field. Take the Heisenberg operator and, I mean, take the general solution of the Dirac equation and interpret it as the Heisenberg operator. So anyway, so these formulas can be derived by just plugging in the expression of the fields into the energy, momentum, and the charge. And so after some calculations, you get these equations. So what's the meaning of these equations? Well, these equations tell us that if we add one particle, so suppose that we start with the empty state and then we create particle by acting with the A operator on the state. So what it will describe a relativistic particle, which is a fermion, which has energy E and momentum P, spin S, which is spin plus or minus 1/2, depending on this label, in the rest frame. And the charge +1. Or actually, Q is equal to +1. The particle obtained with the B operator, well, has all the same stuff, except that it has charge -1. So Q is equal to -1. Now yes.
One thing is, you said spin 1/2 in the rest frame of the particle. So doesn't the S, but we labeled A with an S as opposed to, can S not take on?
Well, S is just either 1 or 2. So it just labels 2 states. So state 1 corresponds to projection +1/2 of the spin, and S equals 2 corresponds to projection -1/2. So there's just 2 projections of the spin. Labels two possible projections of the spin. But we know that in the way that we wrote the solution, this projection takes particular values in the rest frame. Because you can see this spin is not preserved by Lorentz transformations. If you going to some moving frame, corresponds to multiplying the spinner with the square root, and this will produce a vector that has both upper and, it will not be just 1, 0. It will be some linear combination. So this way of labeling states corresponds to them having fixed projection of the spin in the rest frame. Now, okay, so this, well, what are the particles that have spin 1/2, which are massive, and which have a charge? Well, the simplest example is are electrons and positrons, and so this one major application of the Dirac theory is the theory of is electrodynamics. So this field, in particular, describes electrons and positrons. So in the convention where the true electric charge is equal to Q multiplied by the charge of an electron, which is by convention negative, this particle would then correspond to an electron. And then this obviously will create a positron. Let's make it just a 2-minute break.